Okay, so what I wanted to do is I kind of felt like I let you guys down on was it Thursday? Because I did a lot of like talking through the slides but not like showing you anything. And so I kind of want to start again at like slide 13 and kind of go back over some stuff to be a little more clear. And we'll see how far we get. And like I said, we'll see how far he gets. I don't know. We'll see. So, um, so I want to start with slide 13 and kind of show you what I'm talking about with palladium insertions and whatnot. So we've got, so palladium goes from the 0 to +2 oxidation state throughout these reactions. So you start at palladium 0 and you react with some RX group. So R is usually an sp2 carbon, but not always. And then X is typically a halide, usually bromine, iodide, or halide equivalent, so a thing that acts like a halide. So you can have triflate in there as a halide equivalent. Um, chlorine is a halide but doesn't react as easily as bromine, iodide, or triflate. And you can have phosphate, so OP, like OR2. These things all act like halide equivalents. And what happens is the palladium will stick itself in between that carbon X bond, whatever that halide equivalent is, and it will go from being palladium 0 to being palladium +2. So you can think of the carbon and then the halide as both negatively charged ligands. So things that are going to have a negative charge. So to balance that out, your palladium has to be +2. All right. So that's like kind of the beginning of all of these reactions is palladium sticking itself into a carbon halogen bond. Then there is the end of all of the reactions, right? Which is, so in the middle, let's say this, in the middle, you make a bond. So at some point in the reaction, you make a bond, and then you end by doing something called reductive elimination. Really, buddy? See how good daddy is, right? Boom, bottle, boom. So this gets you from palladium +2 back to palladium 0. So this is the last step. You'll make your bond here, or you've made your bond a step earlier. So you go from palladium 0 to palladium 2. Let me go back for a second. You can yell at me. This step is called oxidative. Let's make that actually a letter. Insertion. So when you insert your palladium into that carbon X bond, it oxidizes. So it's called oxidative insertion. And then reductive elimination, you eliminate the palladium and you go from palladium 2 to palladium 0. So usually this looks something like this. I have space for it. I'll do it on the other slide. Right, you have your palladium that'll have it. Oftentimes it'll have two R groups on it. We'll call them R and R1. And the palladium will kind of, I like to say, like step out from being in between the two carbon groups. It will put them together to make your new bond. Plus, it will go back to palladium 0. So it'll lose the negatively charged carbon ligands and just go back to palladium 0. So then this can start the reaction over. Right? So then this palladium 0 can go do oxidative insertion again, and do the reaction. Right? So all of your palladium reactions have these two steps. They have an oxidative insertion, where your palladium goes to palladium 2, and they have, at some point, they have a reductive elimination where the palladium sticks two things together to make palladium 0 again. All right, so slide 14, right, was about palladium choice and ligands. And I kind of got off in the weeds here, but palladium choice, the palladium 0, or starting palladium salt, so usually palladium 2 salt, matters. But it's not really predictable. So this isn't something you have to worry about, like in terms of like looking at a reaction. But what I want you to know is that, like, depending on what palladium source you start with, that impacts how the reaction works, right? So there's nothing for you to stress over in this class other than to know that, hey, if I do a reaction with one palladium source and it doesn't work, I can try another. Because even though deep down you're making palladium 0 in all of your reactions, how you get to that palladium 0 matters. And it changes reaction to reaction. Right. And then the ligands are the same. The ligands matter, but it is guess and check. Right. What I mean by that is you don't usually, you can look at the literature and see what ligand works for a reaction similar to yours, but you really don't know until you actually run the reaction. So you will just have to go through a lot of different ligands before you find one that actually may work for your reaction. So, sorry, buddy, get you off camera now. Boop. So, um, right, you're going to see a bunch of different ligands that get used and a bunch of different abbreviations. In the end, what you care about for the ligands is ligands make the metal soluble, right? I think the example I used before is, imagine if you took, like, or even the Grignard reaction, right, that you did in Organic 2. You threw magnesium metal into the reaction, and the magnesium metal didn't dissolve in the ether until it reacted, right? Palladium's the same way. If you just took a handful of palladium and threw it into your reaction, it's not going to do anything because all your reagents are in solution. Well, your palladium's a solid, so they don't actually mix well. So the job of the ligand is to make the metal soluble, is to keep the metal in solution so that it is around to do the reaction. The ligands impart other characteristics, right? Like they can make the palladium more electron rich or electron poor, or react with certain different things. But what you care about, your takeaway needs to be ligands impart reactivity, but most importantly, they leave the palladium in solution. Right. And so, like I said before, there are thousands of ligands. If we look at slide 15, this is just a small subset of them, right? I don't expect you to know which ligand is good for which reaction. I just need you to know that there are a bunch of different ligands that can be used. That's kind of what the take home I wanted you guys to have on ligands. Right. So I made a new slide, because why not? Called it the anatomy of a palladium catalyzed reaction. Oh, we're losing them now. Okay. Right. And I wanted to kind of lay out the things that you need to look for when you're looking at a palladium catalyzed reaction. Like, what are the things that matter? And then I'm going to show you kind of a sample reaction scheme so you can kind of see where all this stuff is located. So the things you want to look at is, what is the palladium source, right? What did they use to start the reaction? So what is the ligand that they used? What is the thing they used to solubilize their metal, to keep their metal in solution? Sometimes it just starts out on the palladium source. You can buy palladium that comes liganded, I guess, that has ligands already on it. And sometimes you don't have to add an extra ligand because that ligand that's on your palladium is good enough. In my research group, I call PDPPH3 4. It's called palladium tetrakis. I call it baby's first palladium catalyst. This is specifically for you, baby, right? And this is kind of like your stock, most basic palladium catalyst. It already comes with ligands on it, and it works in a lot of reactions. Sometimes it's not the optimal catalyst, but it works. So this is one that, like, the palladium source in this reaction would be palladium tetrakis, right? And the ligands already came on it. Other times you'll add ligands to your reaction, and they'll be listed separately. And then the last thing, of course, we have another slide, right? What are the starting materials? Right, I gave you a whole list of reaction names. The starting material is what you know, is how you determines the name of the reaction. Right. So it determines if you're doing a Heck reaction or if you're doing a what's it called? A Suzuki reaction or a Stille reaction. Those starting materials let you know what reaction you're doing. Right. So that's what you need to look at. So if you look at a, like, kind of a, again, I'm gonna hope you guys are following along on slides here. Oops. So if you look at slide 17, right, this is your, like, kind of stock palladium, like, Heck reaction, right? So you have your RX, so you have your carbon with a halide on it, right? And then a Heck reaction, you have to have a double bond. You have to have another double bond to react with, right? And then usually above the arrow, sometimes below, you'll have your palladium source listed, right? And it'll either be with a ligand or as a salt. So, like, the popular palladium sources that you'll see frequently are, like I showed you, palladium, oh, do it in the right order, palladium tetrakis. Hey, bud. Yeah, it's 2020. You got to watch your professor feed his baby with his chin. So, palladium DBA. DBA is a ligand, but it doesn't, like, do reactions well. So it's often replaced by another ligand. Or you'll see, like, palladium acetate. Palladium acetate's a palladium 2 salt. So the first two are palladium 0 sources. And then the last one is a palladium 2 salt. Right, so those are your popular palladium sources. Then you'll usually list the ligand under your palladium, right? And then you'll have your base, solvent, and temperature, right? And this is going to make a new bond. And I'm going to go over some examples of this before I get into, like, the Heck cycle. I'm hoping that he feeds and then goes to sleep. Then we can do class like normal people. What do you think, baby? You gotta go to sleep? Right. And then you'll have your base, solvent, whatever temperature you ran the reaction at, or all the things that get listed after that. But I think the big things that you need to look for, the palladium source and the ligand. Now, all of these things, if you run a reaction, these are all things that can be optimized, right? You can change the palladium source to make the reaction work better in your particular substrate. You can change the ligand. You can change the base. There are some reactions that lithium hydroxide works really well, but sodium hydroxide doesn't work at all. So these are all things that you have to like check. So, cool. I'm going to try to put him down. So the next one on slide 18 is your typical cross-coupling reaction. So again, it starts with that same Rx, where you've got your halide for your palladium to insert into, and then in these reactions, you have some sort of metal. You have some sort of R with a metal group on it, right? So the fact that you have a metal, that's how you know it's a cross-coupling. Be cool, baby. Right? Hopefully daddy daycare is not too distracting. So the big thing here, right, is you're going to have that same Rx, right? But then you're going to have R1 with some metal on it. The metal is typically on an sp2 carbon, but not always. But the most common ones are on an sp2 carbon, right? And then the rest of it's the same. You're going to have that palladium source. You're going to have your ligand that will get added after the fact, base, solvent, temp. And then this will put together those two R groups and make a bond. So far, so good? Cool. Okay. So hopefully this makes a little bit more sense than it made when I was just kind of rambling on Thursday. So, the basic Heck reaction right? Usually cyclization. Oftentimes you'll use it to make a ring. Is you're going to have some double bond with a halide. And then you'll have another double bond somewhere else in the molecule. And you have your palladium source, and then whatever other things you had to add to it to make it work. And what you can do is you can count 1, 2, 3, 4, 5, 6. And we're going to make a bond from carbon 1 here to carbon 6. All right. So our palladium is going to insert into that carbon-bromine bond. Right. This is our oxidative insertion. This is going to get us to palladium 2. Right. And then what will happen is something that's called migratory insertion. And I have like all the stuff written out a little bit cleaner. So what's going to happen is the palladium is going to make a weak interaction with this double bond, and it's going to hold that double bond close to it, and then it's going to insert, it's going to like make the carbon-carbon bond at this point. So, there's insertion. That was me not wanting to click to the next slide to look up how to spell migratory. So I will look at the next slide and not cheat you. Migratory insertion. So the palladium, migrates. It moves from one bond to another. And as it does this, it inserts itself into that double bond and moves to another carbon. So what ends up happening in this step is we're going to have our ring form. Right, so how we had it counted out before, 1, 2, 3, 4, 5, 6. So come back, right? So those are our 6. So we've got green carbon is now bonded to orange carbon. And our double bond is where carbon 6 was. And now our palladium has stuck itself, is now attached to the carbon just outside the ring. And the key to a Heck reaction is Heck reactions regenerate their double bond, right? So depending on how this works, there are 2 hydrogens the palladium can take. There's a hydrogen here, and there's a hydrogen here. The palladium is equally apt to take either one. You usually would set it up so that there would only be 1 hydrogen for it to take. But since I didn't think this through, the last step is beta hydride elimination. So the palladium has to grab a hydrogen so that it can remake the double bond, right? So I've got my palladium on there. I don't want palladium in my final product. I want to have a double bond. So to make a double bond, you have to remove a hydrogen. So it can remove, the way I have it set up, it can move one of 2 hydrogens. If it removes the green hydrogen, you make this product. If you remove the red hydrogen, you would make this one, right? And when it does the beta hydride elimination, my palladium still has its halide on it. Or I guess it was a bromide. Still has its bromine on it. When you do a beta hydride elimination, the palladium is actually grabbing one of the 2 hydrogens. So you end up with this, where you have palladium that's basically holding on to HBr. Right? Then this is still palladium 2. Right? The last step in all of these reactions is some sort of reductive elimination, where the palladium takes whatever 2 groups it's holding on to and puts them together. So the very last step in these reactions, in these basic reactions, is right. You've got your palladium and your X, and you do a reductive elimination, and you make HBr, plus you regenerate palladium 0, HBr. So the reason that you always use base in these reactions is the base has to get rid of the acid that is generated when you do this reductive elimination. So the more formal, more dressed up version of this would be slide 19, right? Where at the very top, you have your palladium 2 that has to turn into palladium 0, right? So when you start with palladium acetate, the first thing that has to happen is it needs to become palladium 0, because palladium 2 can't do an oxidative insertion because it's already at the +2 oxidation state. Now you have your, then you end up with your palladium that has a ligand on it, and that's the very top of the, let's call it a circle, rough circle, right? And so these are all the steps that I showed with a little bit more detail. So the first step is the oxidative insertion, where that palladium 0 sticks itself into the carbon halogen bond and makes palladium 2, and now you have the carbon and the X group on your palladium. Then the next thing shows the migratory insertion, right? Where your palladium will react with your double bond and make the new carbon-carbon bond. So migratory insertion is where that new carbon-carbon bond forms. So that aromatic ring that I have bonding to the carbon that has R2 and H on it, that's where the bond is formed. And now my palladium is bonded to a different carbon. And migratory insertion is syn, so which means that the R group that you added and the palladium, they add from the same side, right? So you can think of the palladium is putting the carbon group that it had on it on the double bond from the same side the palladium's on. So like the palladium is holding that R group and then dropping it on the double bond with it at the same time. So they end up on the same side. Now, what you have to do at this point is to do an elimination. This is similar to, we're doing an elimination like we were doing an organic 1 with like bases and stuff, but these are specifically syn eliminations, which means that the hydrogen and the palladium have to be on the same side. Right? So if we have my like crappy drawing that I had before, right? Where I have this, right now I have the R group and the palladium are on the same side. So what's shown at the bottom of that slide is I have to, let me use my patent pending arrow here. I have to use my curly Q, I have to turn around this single bond so that one of these two hydrogens that is on this carbon, that is beta to the palladium, so the reason it's called beta hydride elimination, right, is if the palladium is alpha, on the alpha carbon, you're taking the hydrogen off that is on the beta carbon that is one carbon over, right? So I've got to rotate so that my palladium is lined up, is in plane with one of my hydrogens in this example, right? So now I have my palladium and this hydrogen are on the same side. So now I can do that syn elimination. Now the palladium can leave and make the double bond. But you have to rotate your structure so that your hydrogen and palladium line up. If you gently bounce the baby, he will sometimes calm down. I think he wants me to think I have agency over him, but I really don't. But we can try. Okay. So, to make you go back a little bit. Boop. So if you look at slide 11, right, if you look at the reaction that I had done in the thiohaloanic quinone synthesis, right, you can see where the Heck reaction happens. So I'm not going to draw the whole thing. I'll draw part of it. right? So I have that just super stripped down, right? Just this is the part of the molecule that matters, right? And in the end, right, I've got 1, 2, 3, 4. Did I lose the ability to count? I totally lost the ability to count, guys. 3, 4, 5, 6. So I'm going to make a bond from carbon 1 to carbon 6, right, using a Heck reaction, so using palladium 0. And you end up with that 6-membered ring. Indeed, baby. Oops. Green, orange. Right, so there's a lot of other stuff going on in this molecule, right? But the part that is the Heck reaction is just basically forming that 6-membered ring. Everything else is along for the ride and kind of just there to confuse you, right? The part that matters is right there. So again, if I numbered 1, 2, 3, 4, 5, 6, right? And so like we won't break down everything, but if we just look at the beta hydride elimination part of this, right, to kind of bring it all full circle. We get to a point where we have our palladium there, and the palladium only has one beta hydrogen to take from, or one beta carbon to take a hydrogen from, right? So here's my alpha carbon. This beta carbon has no hydrogens. So by how I set up the reaction, I know that the only beta carbon I can take hydrogens from is that one. And so that's how I know I'm going to always get uh, this double bond, because I have it set up that I can only take there's only one beta carbon I can take a hydrogen from. So does that make more sense than it did Thursday? Like kind of the basic thing? Because I just wanted to show you like simpler examples before I got into more complicated stuff. So is this better? I mean, okay, cool. Like I said, so what happened is I felt really awkward switching back between slides and whiteboard over and over and over and over again. And I was like, I'm just gonna pick one, and I picked slides, and I think that was a mistake. I should have picked whiteboard. So I just got sick of switching back and forth. So I was like, hmm. So yeah, that's why I wanted to kind of come back and revisit all this stuff so it could be simpler. So now, like if we look at a more complicated example, right? So like in slide 20, right? You can see what actually matters, right? Is you're kind of counting from the carbon that has the iodide in this top example. You're just trying to get to the end of that double bond, right? So the double bond is like hanging off where the O mom group is, right? So if you count from that carbon, it's 1, 2, the nitrogen makes 3, oxygen makes 4, 5, 6. So you're making a 6-membered ring from the carbon with the iodide to that double bond, and then that's the 6-membered ring you see right beside the aromatic ring in the product. So that's all you're doing when you see a Heck reaction. When you see a halide and then a double bond to react with, think that you're gonna do a Heck reaction, so you're gonna make a new carbon-carbon bond and regenerate your double bond. So the same thing with the one under it. You have the iodide on that beside the nitrogen, right? And you're just gonna count to that double bond. See, that's why I'm sick. babies have like no chill. They'll cough directly in your face. And since it's 2020, you have to make sure it's not the Rona. But I don't think my baby's trying to kill me. He might totally be trying to kill me. But I can't let him know that I know. Right? So if you look at that, if you count from that iodide on the 5-membered ring, you have 1, nitrogen makes 2, 3, 4, 5, 6 to the end of that double bond. And that's the 6-membered ring that you form in the product that like the nitrogen's part of. So that's how you make that ring. So does everyone see that now a little bit easier? I'm just gonna take that as a
Yeah, it's good.
yes. So that's like a Heck reaction. So those are the things you're looking at in a Heck reaction. Right? 1, find your Rx. Find that halide that your palladium is going to react with first. 2, oops, poorly written. Find your double bond. Right? So you need to find that double bond you're going to react with and then count and that's going to let you know how big of a ring you're going to form. The general rule for forming rings still holds true, like from organic 1, right? You're going to form 5 and 6-membered rings faster, right? So in a couple of these examples, right, you could have kept counting and made a 7-membered ring, but the 6-membered ring just forms faster. So you're going to always favor making a 5 or a 6 as opposed to making a, what's it called? Making a 7 or an 8 or a 4. So those are Heck reactions. So let's talk about palladium cross-coupling reactions. Oh no! He did it again. He forgot to share. I'm sorry. Thank you, everyone. Let me find the thing I'm supposed to share here. Boop. Let's go back. Boop. Ta-da! Better? Let me see. Did I miss anything before that? Nope. So this is the first thing you would have missed. All right. So for the Heck reaction, find your Rx, find your double bond that you're gonna make your new bond to, and then count from that Rx to the double bond. And you're gonna prioritize making 5 and 6-membered rings. So let me know when you're all caught up, and we'll truck on here. Sorry about that. It happens about once a lecture now. Okay. And I will, for a second here, stop sharing the whiteboard and give you some joy in an otherwise bleak world. Oh, there we go. I give you organic baby. He is holding The Art of Writing Reasonable Organic Reaction Mechanisms. So he started early. He liked that book so much I had to pry it out of his hands. He's like, this is my book now. This is my life. I'm going to replace you, old man. He tries. He's like, I am pretty adorable, unlike my father. All right. So, there's that. We are fixed. Okay. So, palladium cross-coupling reactions. Right? So, there's a couple different reactions that fall under this category, right? Right? So there are different reactions that count as a cross-coupling reaction. So like the list that I had given you before, let me go make sure I don't forget anything. Right? You have the Stille, the Negishi, which I don't know why I wrote an M there. The Negishi. Kumada, Suzuki, and Sonogashira. You're not a fan of the Sonogashira reaction, buddy? I'm sorry. So these first three, basically, 100% their mechanisms are like all the same. The thing that differentiates Stille, Negishi, Kumada is what metal you start with, right? So the name depends on what metal you're using as the other part of the reaction. So like Stille, you use tin. Negishi, you use zinc. Kumara, you use magnesium. I am like 100% sure. There we go. Right. Suzuki has oh my God. I'm so great at technology, guys. Like, I'll show you a picture of the baby and then forget to actually do my job. And that's a really bad Z for zinc. We'll fix that Z for you. Oop. At least you haven't yelled at me that my mic's been muted, so that's good. I haven't fallen into that old person on Zoom trap yet. So, Stille, tin, Negishi, zinc, Kumada, magnesium. Suzuki has one extra step in the mechanism, but otherwise it shares the exact same mechanism as the first three. And this uses boron. And then Sonogashira is kind of doing its own thing. And it uses copper and triple bonds as opposed to double bonds. But the first four basically are all the same mechanism. So as opposed to showing you the mechanism for each of them individually, I'm just kind of lumping them all together, and I'll just show you where the difference lies. Right? So kind of your basic mechanism for these. Right? You have again, you start out with your whatever your X group is, your halide or halide equivalent. So basically I'm walking through slide 22, but we're going to do it step by step and a little simpler. Right? And again, your palladium is going to insert into that carbon X bond and get you that same palladium species that we had before. Right? So this is our oxidative. Oops. Is it A? Right? That's your oxidative insertion. Right? Now, there's not a double bond to react with in these reactions. You've got a group that has a metal on it. So instead of having your R1 on a double bond, your R1 is on a metal. So this basic mechanism works for tin, magnesium, and zinc. So in this case, Stille, Kumata, and Negishi. And so what happens here is something called transmetallation, where you replace, where palladium replaces the metal on that R1 group. So this step from, this is transmetallation. Hey dude, you've been killing it. 25 minutes? Can you give me 25 minutes? Maybe. All right. So we do our transmetallation. Now we've got our palladium. Again, this is palladium +2, right? Palladium in the +2 oxidation state. And now I want to put those two carbon groups together. I want to put my aromatic ring that I have together with the carbon, like our R1 group, right? And this is the reductive elimination step. Right? So here is where you take your two groups and you put them together, right? That spits out the product. Plus, it regenerates your palladium 0. So you go from palladium +2, you make the bond that gets you to palladium 0, gives you your product, and regenerates your palladium to go do this reaction again. Absolutely. Sure, no problem. So if you look at the catalytic cycle on slide 22, it's the exact same thing I just showed, right? But kind of all wrapped up where it just like loops back around to making palladium 0 again and just starting the process again. Oxidative insertion gives you your palladium with a carbon and a halide on it. Transmetallation gives you a palladium with 2 carbons on it. And then reductive elimination gives you your product and regenerates your palladium 0. So some examples, and this first one is really big on 23. So they had this great big molecule, and they had 2 iodides, the one on the left and the one that's kind of like on the right and up. And they mixed this together, and they did the reaction overnight, and they got the product to form in 62% yield. So they were able to have the Stille reaction occur between the two different, what's it called? The two, the iodide that was closest to the tin as it was drawn in the structure. I worked with a faculty member, well, worked with a faculty member when I was a grad student, was in this lab when this reaction happened, and he said, well, none of us thought this would work. We just came in and we're like, oh, amazing, right? And then they do the same, then they do a similar reaction again, where they have another tin compound, and then they have it react with palladium again, and they get the product, right? Where you have the iodide in the structure that was the product for the first reaction reacts with the second alkyl tin species to give the product. Now, again, there's a whole lot going on this slide, but the thing to take away is, right, you're going to find your metal, your our metal, and you're going to find your halide, right? And that's where your reaction's happening, right? So kind of similar to the Heck reaction, right, for cross couplings. Right? Step one, find your Rx, find your halide, find the place that your palladium is going to insert itself first. That's going to help drive you kind of figuring out what the reaction is going to do. This one's a little different because there's two halides, and I think that they would admit they got a little lucky. Right? Next, find your RM. Right? Find your spot that has the metal, and that's where then you're going to make your bond, right? You're going to always end up doing something that looks like, right? Right. So there's a lot going on this, but you could just say, like, I have an iodide, I have a tin, right? I found my iodide, I found my metal. I know at the end of this reaction, I'm going to make a bond between the carbon that had the iodide on it and the carbon that had the tin on it, right? Someone thoroughly agrees with that, right? And it doesn't really matter what else is attached to that because these are the two functional groups that are going to react, right? You're picking a reagent, palladium, that is very specific for reacting with an alkyl halide, and in this case, a tin on an sp2 hybridized carbon. So it doesn't matter what else is going on in the molecule. You can simplify this reaction down to just finding those two things and putting them together. So kind of regardless of what else is going on, you can strip everything down to just the very basic part of it. So you can look at something that's big like this and go like, okay, all that stuff's cool, but the part that matters is the iodide and the tin. So the Gishi reactions are similar, but instead of using a tin, you are replacing that tin with a zinc. And what's nice about the examples that I have picked for this is that the first step in both of these reactions on slide 24 is, well, it involves a lithium. So this top reaction here from Organic Letters 2005, right? The thing that's reacting is you have I'm going to strip it down, right? You have this halide, right? We don't need to draw the whole thing. And it's getting bonded to, or it's reacting with, this lithium, right? But it doesn't actually react with that lithium. What happens is we have to make a zinc containing compound, right? In the Gishi reactions, you have to have a zinc as your metal on your sp2 hybridized carbon. So the first thing that happens is this lithium reacts with zinc chloride and attacks the zinc, knocks off a chlorine, and generates your zinc chloride that way, right? So you end up with your zinc because your lithium can react with zinc chloride. So as opposed to, like, you can't buy alkyl zincs or zinc reagents in general that are complicated because organo zincs are kind of like Grignard reagents. They're hard. They're very reactive. So we have to usually make them in situ. So we have to generate the zinc reaction in our flask, we have to generate the zinc reagent in our flask and then use it immediately. You can buy simple zincs like diethyl zinc, dimethyl zinc, but was it one of them or both of them catch on fire as soon as they're exposed to air? So um, it's usually just best to make the little bit of zinc reagent you need in solution and then use it. So here they take an organolithium like we talked about earlier, right? Have it react with the zinc, and then they can do the cross coupling. So then they have their bromide and they have their zinc reagent, right? In the next one, the first step that they do is something we talked about before, which is they do a lithium halogen exchange, right? So they have a primary iodide and they treat it with tert-butyllithium. So tert-butyllithium is basically able to switch a lithium for any halide that it sees. So you have tert-butyllithium, which is the fastest for doing lithium halogen exchanges, and you have an alkyl iodide. When iodide is the fastest for doing lithium halogen exchange. So those two things together kind of get past the fact that you're making an sp3 hybridized anion, and then that reacts with zinc chloride to make the zinc species that's shown. And then that is what reacts with the iodide and the palladium shown in the next arrow to give the product. So you're able to kind of do a lithium halogen exchange or lithium reaction in the first example, but generate a lithium so that you can generate then the zinc, because it's harder to make the zincs any other way. That good? I went a little talky there. Cool. All right, and then we have Kumada couplings, which Kumada couplings are all the same except for, oops, spelling. So Kumada couplings use Grignard reagents. So their metal is magnesium. So it's doing something where you take your halide and you react it with a Grignard reagent and palladium 0, and that will make your new bond, right? So this guy is this guy, and this guy is this guy, right? So that makes your new bond. So as opposed to using a zinc reagent or a tin, you're using a Grignard. The advantage here is like simple Grignards are really easy to come by because it's really easy to make a Grignard reagent. I think you literally all have made a Grignard reagent in your life. At least everyone I had in lab did, for sure. Right? So you've all made a Grignard reagent at some point. So you know how easy they are to make. So, or you can just buy them. So they have that advantage of just being easy to come by. So, right, this first example, they just use a simple vinyl Grignard reagent that you can just buy, and they react with that iodide, again, in presence of palladium tetrakis, and they make their double bond, they make their new bond. And then here, they're using an sp3 hybridized Grignard reagent, and they're reacting with the vinyl iodide on the left, and you can see that they make their new bond, and then are ready to go on to further steps. So the Grignard reagent, the Kumada coupling is pretty useful as well. Usually, like the advantage of like a Stille reaction is alkyl tins or aryl tins. You can just buy those. Those are just something you can go order, and they're relatively stable. So you can just buy them and take them off the shelf Negishi and Kumata couplings, they are things that the metal portion is really reactive. So if there was an alcohol in either of these molecules, you'd have to protect it, like they do in the second one. They protect the alcohol as the OTBS, so the Grignard reagent doesn't react with it. Where like the Stili is not that carbon tin bond isn't basic. So there are some like pros and cons to each of them. Like a major pro to like the Negishi, Kumata, and the Suzuki we're going to talk about is none of those things, zinc, magnesium, or boron, are toxic, but tin is super bad for you. So, like in my research lab, I try to avoid doing Stili couplings because just the byproducts are pretty toxic. Whereas doing a Suzuki reaction, the byproduct is basically borax. So it's not as bad for you or bad for you at all. So I'm going to do this. I'm going to do the Suzuki cross coupling, some examples first, and then I'll show you the actual like mechanism. But we'll go to the whiteboard, or we'll stay on the whiteboard. So for a Suzuki, the big thing here is your starting metal. So these use boron as the metal, right? And you may be thinking, well, boron's not technically a metal, it's a metalloid, and this is true, but it acts enough like a metal for in this context to work. So just like all the other ones, you're going to have your halide, and then you're going to have something that has some boron reagent. So oftentimes it's a boronic acid. So this is a, oops. Someone's reaching the end of his like ability to be good. But he's 3 months old, so like I'm surprised that ability is like anything longer than 2 seconds. So, right. And again, we're doing the exact same thing. We're like taking halide and sticking it to a group that has a metal. So we're gonna actually try to get this to fit. Right. So we're gonna have this and this, and this uses palladium 0. But you have to use a specific type of base to make these work. So you have to use some sort of hydroxide. So I guess you could just call it OR. So hydroxide or alkoxide. So it has to be sodium hydroxide or lithium methoxide. You have to have some O minus as your base to make this reaction work, right? So the other cross couplings, your base could kind of be an amine base, triethylamine, or something like that. But you specifically have to use hydroxide bases for Suzuki reactions because the hydroxide activates the boron. So OR minus. So boron doesn't like to transmetallate. Just if you have this and just palladium, it doesn't like to transmetallate. That reaction either doesn't happen or is pretty slow at best. So you have to have, so just this gives no transmetallation, right? You have to have base present. You have to have hydroxide present or alkoxide, and then you can do your transmetallation. Well, sorry, this should be palladium 2. Palladium 2. Sorry. Palladium 2. Right. And that will get you your transmetallation. And you end up making in this case, boric acid or borax. So what the hydroxide does is you have your boron-containing compound, and the hydroxide attacks the boron. So if you remember, boron has an empty orbital, right? Boron's the oddball on the periodic table where it only has 6 electrons around it. It doesn't have an octet. So you have to you're able to add hydroxide, add that O minus to the empty orbital on boron, and this makes something called a borate, right? Remember, ATE is just how we like signal that we have a negative charge on something. So borate is just a boron with a negative charge. And the borate is what's actually able to do the transmetallation. So now this, when it reacts with palladium-2, that's what transmetallates. Hey, is the borate, not the boric acid. Right? Another starting material you can use in Suzuki reactions is not a boronic acid. You can use a boronic ester. And the difference is, everyone good with this slide? I don't want to go too quick. Okay, no. If Caitlin's good, we're all good. That's how I live my life. Right, so this is a boronic acid. Oops, OH. Right, and that the acid part of it is the OHs, right? You can also use boronic esters. And this is similar to just a carbon ester, right? I replaced OH with OR. So it's the same thing as going from a carboxylic acid to an ester. You replace the OH with OR. So I think I'll go through the catalytic cycle. I can go through the catalytic cycle, and then we'll just start on the Shonagashira reaction on Thursday. So this is, so if you look at slide 27, this is the catalytic cycle. Again, kind of a cleaned up version of what we just walked through. So the palladium reacts with the RX, our halide, does oxidative insertion, goes from palladium 0 to palladium 2. Then it does then it does, they call it a metathesis or whatever. It loses a halide and becomes OR. Then it transmetallates. So it swaps, it replaces the boron with the palladium. Then we do reductive elimination to generate our product, and then generate our palladium 0 again. So basically the same thing as the other one, except for in the middle of my little circle, right, is the step where the base has to react with the boron to make the borate, so it can actually transmetallate. So I think with a baby ready to explode, that this should be a good time to stop. You want to say goodbye to everyone, buddy? Does anyone have any questions? You guys are awfully quiet, other than I was like, are you good? Guest lecturer Gavin is here to answer all your questions. Hello. Awesome. Okay. You guys are free to go if you feel like you understand what happened today. And I guess I'm gonna have to throw the video up on YouTube for Tyler to look at since he is AWOL. Huh. This is Gavin the baby. Yes, this is Gavin Lewis Wakefield. Thank you. He's less cute like when he wakes my wife up in the middle of the night, but he is pretty all right. He is 3 months today. He is. He might be 3 months, like literally this instant, like exactly 3 months. Because I think he was born at like 10:40 on Tuesday. Say, happy 3 month birthday, baby! Yay! All right, you too. I'm gonna go try to find a COVID test. Yay! You too. Bye. See you guys. Sure. Say bye. Say bye bye, everyone. Bye bye. Oh, everyone left. He's like, Gavin. Say, Gavin the baby. What up, everyone? I'm Gavin the baby. Okay, buddy. Let's stop our share. Let's stop our record.